Okay. Yeah. You got to work now. That's good. Can everybody hear me okay? Cool. Show of hands, how many people know what an HTAP database is? Fascinating. All right. So let me start with that. So the database market is starting to converge. And what that means is that your normal transactional systems and your analytical systems are no longer completely isolated from one another. Commercially, this has been Oracle Exadata and SAP HANA are the two kind of dominant database players in this market. Why is this emerging? Generally, people are starting to build more and more complex Lambda architectures to do things like this, where you can do both real-time and batch. And that's starting to phase out into a single system to be able to do that. So what are we? We're a cloud database. We run both in the cloud and on-premise on Hadoop platforms. We have ANSI SQL. We support indexes, joins, procedures, constraints, UDFs, triggers. What's different about Splice Machine than your normal kind of SQL on Hadoop or even Spark SQL? We're really about data management. So what does that mean? We're doing check constraints, triggers, foreign key checks, things that an operational database would do. So Splice Machine is capable to run a real-time application. So if it's a web application or order management type application. Current architectures that are falling down right now look about like this, where you have a bunch of systems of record, they ETL to an operational data store, then you have kind of your mixed workload apps, usually marketing type applications, and your operational reports and analytics. And what's happening is this is way too expensive as you scale out the number of records. So modern applications require a new data platform. You have to couple OLTP, which is basically your windshield, what's hitting you right now, and OLAP, which is your rear view mirror. Does that make sense generally to everybody that these two things have to start coming together? The way I describe it to people is right now we have really dumb interactive applications and really smart analytics that doesn't interact with anybody. And we're trying to figure out how to build these smart applications. So what does that mean? The challenge here is that a lot of people have built, analytical engines, for example. And a lot of people built transactional engines, and they're separated. They're different. They have different storage options. Transactional systems generally are row-based storage, like Oracle, Postgres. And then you have analytical systems that really do the best, like Vertica, ParExcel, that do that on columnar data in a columnar storage format. Now you can imagine a database that can take the SQL and make decisions based on what you're trying to do and go either to a columnar type structure or a row-based structure. On top of that, the compute engines are completely different as well. It doesn't make sense. So in the case of Splice Machine, we use Spark for our analytical data flow and compute engine. I'll get into the nitty-gritty of that. But it also doesn't make sense to use Spark if we're trying to do a single row lookup or if we're trying to do a quick nested loop join to run an application. So we try to bifurcate those two capabilities. I'll quickly go through use cases just so you kind of get a sense of, well, what are you guys actually doing out there in the market? Big things are digital marketing, supply chain optimization, financial services, because they have a lot of large data sets that they still want real-time access to. So here's just an example case study. I'll just do one of these so that you get a sense, and then I'll get into the technology. This is Cetera Financial Group. This is a classic operational data store. You're wanting to take data from a bunch of different places. You're wanting to put it together. But the thing that makes it special is that you actually want to hook applications up to it. One of the things that always jumped out at me is that when we look in this big data space and the distributed computing space, there's been a huge chasm between actual applications and being able to work on that platform. That chasm is narrowed with at least with regard to business intelligence applications. But it's got to narrow even further so people running a mobile application can access that massive data store and retrieve your records to show in a mobile application, and also be able to analyze your records in a machine learning library. So how do we do this? Pretty straightforward. So the first product that we really use is HBase, which sits on top of generally on-premise HDFS, or if it's in the cloud, it can sit on different file systems for the different cloud vendors. We used Apache Derby as our initial prototype when we started out, and we've amended that parser quite a bit. So when we talk about HBase, how many people know HBase? Okay, great. So HBase is nice for a scale-out architecture. The key thing here is it's called an LSM tree, log structure merge tree. So data comes in, it's appended to a write-ahead log. As it fills in memory, it's then flushed to disk in a sorted fashion. Our implementation and how we do HBase, we do it with a row-based storage. So when you look up data, you look up a key value, it'll have all the data of the row there, you return that back. That's a low latency access. So to grab a row, you're talking 5-10 milliseconds sort of thing. So something you can run a mobile device or a website on. Cool things, it's auto-sharded, so as you keep putting more and more data in, it'll start splitting the data and laying it out for you. You don't have to do that. It scales with commodity hardware. It has high availability, so as you fail, it'll bring it up on another node. So it's got great capabilities. So the question I always get, well, okay, you're using HBase, why do you need to use Spark? And we use Spark for several reasons. First, HBase had problems, and actually all storage infrastructure, especially key value store, have problems. Most of the problems that they have are things called compactions or cleaning up data. So generally people err on writing really fast, write it to the file system really fast, and they have processes that come along every so often and clean up or merge files. It's a common practice. Kudu has it, HBase has it, a lot of different key value stores have it. The challenge is, for like HBase as a key value store, is when you want to try to make this operational, where you know how long the query is going to take. When it runs compaction in HBase, it's like a heart attack to the system. The system starts to slow, it becomes completely nonlinear in its behavior. So what we did is we took that compaction process, and instead of running it in HBase and causing all kinds of known problems, we took it and ran it in Spark. Because Spark gave us resource management, it gave us containers, either through Mesosphere on the cloud or through Yarn on premise. So it gave us containerization. So that was a big thing for us. We also, any large data movements in our system, backup, anything where you're moving a lot of data, we run that through Spark so it can be scheduled against other things that are going on in the database. We added RDBMS features for that. So when we create an index, we actually read the table from Spark, and Spark actually reads it and then writes it into HBase ultimately. Statistics, and I'll go through that. That's one of our more advanced features that we have. Import, so when we import from files, we don't read it from HBase, we read it from Spark. That's all scheduled and fair scheduled for those activities. And we also can support external tables. So using some of the Spark libraries, we can read Parquet, Orc, any kind of files off the file system, which is pretty powerful. The big reason why we chose it was analytical processing. I think we take for granted how powerful Spark is with its directed acyclical graph and being able to recompute when you have task failure. That's actually a really hard process, and most databases internally have to build something like that. And it's ultimately, what do you do analytically when you have a shuffle of data that's too big and it needs to spill to disk and you have multiple tasks operating on data? So we chose Spark for our internal data flow engine. If anybody's got questions, please just yell. We also used it for stream processing. So people can start up queues in Splice Machine, read from Kafka, and actually execute SQL against those things in real time and do it in a transactionally reliable way. Machine learning, we incorporated mlib into the database. So when you run SQL, you can put a machine learning library right on top of it, And the whole thing is packaged as a Spark instruction set, which means it's completely reliable. It has all the task failure handling and everything. Something nice we did. And the thing that's really thing we take for granted at Splice Machine is operations of this. So when you want to run a large analytical query, it can spawn yarn executors based on the topology of your Hadoop cluster, or it can, we use DCOS for our service, but you can also start computing containers for executors to execute tasks in more of a cloud platform. Really powerful ability to scale elastically compute away from storage. Here's an example. This is what compaction looked like and the response rates in HBase when compaction was run actually on the HBase process. And by moving this to Spark, this line is straight now. This is actually what was happening. And to today, most people still run compactions in HBase. But this is what happens to your response times. So for us as a relational database, it's hard to tell someone who's going to use us, yeah, we'll probably be 2 or 3 milliseconds, but we could be all the way up to 25, depending on what's going on in the database. So this was a really powerful problem. The second part was, well, we know compaction's going on, but it was kind of a back office process, and we never really understood, well, how many files are being put together, how much memory is being used, what's going on. So we modified the Spark UI, and we pass in different parameters to that. And then all of a sudden, now when you click on the Spark application, you can see if you're running minor compaction or major compaction of your key value store, how many files, what was this is an index for TPCH, it's just an index table that's being, how many files, 5, total size, 242 megabytes. And you can actually see the process of your key value store cleaning up. So we really use Spark as the way we do all scheduling and all large analytical movements. So it gives you, as an administrator, a common framework to look at and say, oh, okay, I know all the tasks that are running on my database, I know the resources that are being used, and that is an elastic compute infrastructure. Second thing we did, which I think is pretty innovative, Google also did this actually with Bigtable. But what we do is Spark, what's the best way to say this? When Spark runs usually against like an HBase or some other storage solution or an RDBMS, it usually pulls the data from that process into Spark. And that's generally a slow path. In our case, what happens is when we want to read data from HBase, we actually read it through the file system. So we go directly to the file system, and then we do incremental deltas with the data that's in flight in HBase, so that we still get consistent reads of the data, but we don't have to hammer HBase trying to read all the data through HBase. And that's generally, from what we've seen, about 100x speed up in time. So does that make sense? So instead of looking at your key value store and saying Spark's going to read from the key value store, that's not really ever scalable, because you have one process reading from the file system, which is a fast process, and then you have Spark, which is a Java process, reading from another process. And that process-to-process communication will never work in an analytical system. That's something that people try to push away. What they generally want is their analytical tasks to run directly against the file system. Why? Because file systems scale, they're fast, and it's a really fast access path. You're just loading blocks in. So hopefully that makes sense. So what we did, we avoided the HBase API, and we wrote our own API where we go to the store files that are out there, just what HBase is looking at, and then we do incremental deltas from what's in the mem store, i.e. the in-flight data, to get a consistent read. And then we also control splitting while that's happening, so you're not reading files that are no longer valid and those sorts of things. Second thing we do is we implemented a universal bytecode generation. So we do universal bytecode generation both for the OLTP and analytical side. What does that mean? If you do something like, I want to where clause like equals percent something, it's advantageous to be able to actually put that in bytecode and optimize the data going through that. And you'll see that all through query planners. They want to optimize the bytecode. So what is I'm going to go through this really quick. So how does this work? And that's what I always hear. So the first thing we do is parse the SQL. So you send SQL 99 in, generates an abstract syntax tree of what the plan looks like. It binds it to a transactional dictionary so that you can have dictionary changes in Splice Machine, transactionally reliable. So if somebody's altering a table over there, someone can still be running queries on in another client. Second, what do? We determine the access plan. So should we use the base table? Should we use the index? And what join algorithms should we use? Should we use a broadcast join where we move the data to each node? Should we do a merge sort or sort merge join? Should we do a hash join? All of those decisions are made by the optimizer. And it's all based on cost-based statistics. So our focus is Splice Machine, and one of the things that we do, I think, pretty well is we base the flow of I'm just going to put that all out there. So our cost-based statistics will tell you what plan to run. And I'll go into more detail into our cost-based statistics. You generate the bytecode, and then based on the cost, how long you think it's going to run, you either run it in memory against HBase, or you send the instructions to Spark, a data frame of instructions to Spark to execute. So does that make sense? So if it's an analytical query, it'll say the cost is really high, run it in Spark. And if it's just like somebody trying to grab a single record or single record lookup, that'll run against HBase. So that seems really easy, right? Seems kind of clear. So this little decision, most companies, what they would do is they would have replicating the data to two different places, or some sort of Lambda architecture to be able to handle this, to handle both real-time inserts and updates, and at the same time be able to run analytical queries. And these systems are different. So for a real-time system, it's all about block cache, right? Because you don't even want to read from disk. You want it in memory. You want to quickly access it, or at least be in memory in the operating system. And use Bloom filters to see if you even have to look at files. This is really optimized for single lookups. So it makes sense that that's your kind of transactional model. That's really appropriate. When you get on the Spark side, you don't care about block cache. You're going to blow through that anyway. It's a big table scan. You're really more focused on, can I get it scheduled? Can I do it in a fair scheduling? So if somebody has a massive query, it doesn't dwarf somebody doing a quicker analytical query. And that's kind of the big piece. And can you do it in a reliable fashion? So as you start running bigger and bigger queries, if tasks fail, can you keep running through those? And the key thing that Spark gives us is this. It's the fair scheduler. So when you submit queries or index updates or anything of the like, you can say what's the weight of those tasks versus other tasks. We also optimize the UI so that it will actually show you the query plan that you're running and the cost and how much data you're going to be reading. So as the query's running, you can see here's what the optimizer thought. This is how many rows the optimizer thought would come back. And here's actually how many came back. So we have accumulables that show you how many came back as the tasks finish. So it's a very interactive, nice user interface. And I don't have a ton of time, but one thing I do want to share with it, and I try to share this with everybody, statistics. This is a hard thing to say. To do analytics, you need a cost-based optimizer, and you need really good statistics. What does that mean? Your cost-based optimizer has to go through join order and join types and all the ordering of tables, and do query unrolling and those sorts of things. And your statistics have to go all the way to histograms so that you understand how much data is coming back in your queries. Because some joins are not feasible. So I could be querying a 2 billion row table, but if I'm only returning 100 rows, for example, it's perfectly logical to do a broadcast join of that 100 rows to all the nodes. But if I'm going to return 1 billion rows from there, well, I can't do that. I'd take down all the nodes because I'm pushing too much data around the network. So this is absolutely critical. And we partnered with Yahoo, and we built upon their sketching algorithms. So we used their quintile algorithms, their frequency sketch, and their theta sketch. And what's really powerful about these is that they're composable. So you can run it on a shard of data here and a shard of data here, and it's really easy to put the two algorithms together and the error bounds, and then you can actually see and run, and you can actually computationally know how many unique elements, how many elements based on the histogram that you're querying. So this is absolutely critical. So if you don't have statistics, generally what happens is you have an unstable system. So when you look at databases, make sure you look, or even query engines, make sure you look at their statistical capabilities. Because if it's just like simple counts or something like that, generally you're going to be unstable. Hopefully that makes some sense. Second thing we did with our encoding, we actually implemented Project Tungsten for our row-based storage. And we have some modification of that we've used. What it allows us to do is map from our rows of data directly into the bytes so that we don't have any sort of serialization, deserialization cost. We do this for our row-based structure. Our columnar structure, we usually use Parquet for that. Talk a little bit about hybrid storage, row-based and columnar, how important that is. We do use some in-memory caching. We allow you to pen tables, so that actually puts the data frame in memory in Spark, allows you to play with that. It's more of an experimental feature, but we do that. That's what I had, and I wanted to make sure I have time for questions if there are any. If you want to try it, go out to AWS. We have a sandbox. You can spin up a cluster. We also have a community site. You can go to it, and we're open source, so feel free to download it and start running the database. All right, thanks. Any questions?
Can you go back a couple slides?
Sure.
You had your first 3 steps, and then you made a choice to go HBase versus Spark.
Yep.
And I think yesterday, Ho and Wei, I think those were the two. Oh, I'm sorry.
No, it's all right.
Yesterday, there was a presentation by, maybe it was Ho and Wei, about changing the catalyst optimizer. Mm-hmm. It's interesting, so that in 2.2, Spark would be making better choices about query plans, join order, and so forth.
They've got a lot of work. So they don't, right now, Spark is a rule-based optimizer. So that's challenging. Then you have to go to a cost-based optimizer. And to go to a cost-based optimizer, one, it's hard as heck. I mean, it's not a small undertaking. Second, you have to understand how you're going to traverse the solution space to come to the optimal plan. And that's a complex process as well. And the thing that really trips people up is the statistics piece. So if somebody's going to do that, you have to say, well, do you have cardinality estimates? And if they say no, you say, that's not going to work. Because the literature is pretty clear. It's really hard to run an analytical, any sort of SQL without cardinality estimates.
So what I'm wondering is if I'm doing analytics,
Yeah.
out of the box, I currently get poor performance because the query plan is just not suitable for my queries.
How many joins do you have generally?
Yeah. Many joins.
Yeah, once you go there, yeah, you're going to you need something that
If I
has...
use this solution and I solely go the Spark path, will I get better performance?
Yes, you'll get better performance. And the reason why you get better performance is not, we're using the same APIs as Spark, it's just our optimizer is doing a cost-based optimization, and we piggybacked on, and I can't mention this enough, these Yahoo statistics. So it actually gives me a histogram. So when you put in your where clause, I know precisely how much data you're pulling back. So I can do optimizations like broadcast data, or I can merge data and do other things. If you don't have that, and we do that both for columnar data and for row-based data, but if you don't have that, generally it's hard. It's a hard run. And these are what, like a Vertica or Teradata, those type of companies, this is kind of their bread and butter. And a lot of the nascent technologies are still kind of catching up on that. But yeah, that's exactly why you have problems. When you get up to, 10, 15-way joins. No, it's hard because it's a huge solution space, and without a cost-based optimizer, rule-based optimizers completely fall over at that place. Yeah. Cool. Yeah. Well, thank you.
Thank you very much.
Yeah.